Hello everyone, I'm Praveen, and in this video I will be discussing the modeling and computational fluid dynamics analysis of a two-dimensional laminar flow between two parallel plates in ANSYS Workbench. And upon opening the ANSYS Workbench, you get this interface. And since we have to do the CFD analysis, so we'll click on fluid flow fluent. And upon clicking this, box will appear with what all we have to do with that. So it's opening. It will take some time to open. Okay, here we go. And the first step would be to modeling it. We'll make the geometry. We'll then mesh it, and we'll go and give what kind of materials we want and what all the boundary conditions are. We'll define the domain, and we'll then go for we'll calculate the solution. Upon converging, we'll show the results. So let's go to the geometry. We'll double click on geometry, and okay, we'll wait till it opens. So now this is design modular. We will be first draw the sketch. So we'll click on sketching, and then we'll click on rectangle. Click here. We'll drag the cursor. And this is the rectangle. We'll then go and set the dimension of this rectangle. We'll click on dimension and then on general. We'll click on one side of the rectangle, drag the cursor side. We'll keep the length 1 meter and width equal to 0.25 meter. So our sketch is ready. Now we'll form the surface out of this sketch. We'll go to concept and then click on surfaces from a sketch. It is asking us to choose a sketch. We will click here on one of the edges of the rectangle. We'll click on apply, and then we can generate the sketch. Now the sketch is ready. That's great. So the geometry part is over. We have specified the dimensions here. We have made the sketch. Now we'll exit the design modular, and this geometry will be saved for use in later stages. So we'll exit it. Now you can see the green tick here, means the modeling of this surface of the plate is over. Now we'll go for meshing. So we'll double click on mesh. Now you can see here in the left bottom corner it says starting meshing. So till it starts, we can wait. So I'll be pausing till it opens. This is the meshing interface. You can see that geometry has already been imported. So now we will right click on mesh, and we will then insert sizing. click on and press Control and choose these two edges. Actually, let's all through and apply. Okay. Now we'll give the element size. Here, there's already a default value given, so we'll change it and give it 0.01. And I'll upload the mesh. Okay, just we'll give name all the four boundaries. Define this age and then right click and create name selection. We'll name it inlet. Okay. Okay. This would be outlet. And then wall. Wall as well. Okay. So we have named different edges. We get the edge sizing. Now we'll generate this. Let's generate it. See the progress here at the bottom left. It will take some time. Since in meshing, actually, we subdivide the entire geometry into different elements. So this is the default mesh that we got. A mixed mesh of triangles and triangular and rectangular elements. So we'll change it to, we'll go for face meshing and put more region. We'll select the entire geometry, apply it, and then break it. Break the mesh. Mesh will get updated. Okay, it's done. It's great. Here the dialog box also says that the mesh transition is successful. Okay, so the meshing part is done. Now we can exit this interface and go for the next step. So we will exit it. Nothing more to do here. You can see a green tick here that the meshing shows meshing is complete. Now we'll double click on setup. And you can see in the bottom left corner it says starting point. So we'll wait till it opens. Solver setup is now done. This is the interface. So in this general section, we'll first check the mesh quality. We'll click on, and if it says done, then everything is okay. Now we go to models, and since it has been specified that the flow is laminar, So we'll change the flow to laminar, discuss laminar. We'll click on laminar and then press OK. We'll leave these options as they are, and then we'll go for the material selection. Fluid, where the fluid is air, and I want to change it to water. So we'll check that in Fluent database. The database is open. Selected water liquid, fresh copy, and close. So water liquid is selected, close it. Okay. Now the fluid is water. The solid, the default one is aluminum, and we'll leave it as it is. You can change it if you wish to. And with this one condition, so those should be true. So it's water liquid. Apply it. Check it out. Double clicking. It's water liquid. Okay. Now material selection is over. Now we'll go for defining the boundary conditions. At the inlet, we'll give the inlet velocity. Okay. So give it to the 0.01. Apply. The options will remain as they are with the default. Now we'll go to the solution section. We gave the boundary conditions. Material selection is done. Before that, okay, and then in solution and methods option, we will leave the default values. And monitors will go to visible. Now you can, the convergence criterion, you can do it none or leave it absolute. What absolute does is, once these values are satisfied, okay, once it start converging, then it will stop there itself and won't complete 1000 iterations, or the whatever number of iterations you have specified. Okay, and if you click none here, then it will complete 1000 iterations, or whatever the number you have specified. Whether it won't matter if convergence has reached or not. So we'll keep it absolute and just make it a little more accurate. So okay, and we'll now go to initialization. There are two options: hybrid initialization and standard initialization. So if you click on the standard ones, you'll have to manually give in the initialize the values. So we'll go for hybrid initialization. We click on initialize, and it is initialized. Here you can see hybrid initialization is done. Now we'll run the calculations. We'll double click on run calculation. Here we go. The number of iterations, let's take it 1000. Yeah, it will take a little more time. It may not go for 1000 iterations. I mean, if it reaches convergence much before that, then it won't take that much iteration. If it does not reach the convergence, then it will complete 1000 iterations. Okay, so now we'll click on calculate. You can see here it will start doing the iterations. It takes a little more time in my system. Maybe it requires a better processor and more RAM, a faster function. So we have reached convergence. And it says that this dialog box says the calculation is complete. And let's see how many iterations has done. In just 56 iterations, we can read it here. The solution is converged. So it converged in just 56 iterations. Had it not converged, it would have taken more iterations. Okay. So this is the graph, how the velocity changed with different iterations. Now we'll go to the result section. You can see the result here, or from the workbench interface, you can go and get the results. So we'll go there and see the results. Okay. You can check it here also. Let's see, you want to see the contours of velocity. Okay. So we'll save in display. So this is the distribution. Let me zoom in. You can see the velocity near the plate is less, and as we move towards the center, it increases gradually. That's quite beautiful. Okay. We can check the pressure variation as well. This is even more beautiful. So this is the pressure distribution, okay? At the outlet it is quite less. At the inlet it is action, which is opposite. You can see other properties as well. This is the variation of density. Okay, so we close this, and you can go to the plots. Different plots are there, and you can draw X-ray plots. The velocity variation, you can choose the variation along the surface body. Plot. This is how it is varying. Okay, so we'll go to the result section and see what more can be done. So we're closing it here. So solution part is done, and we show the results as well here. We'll go and check in the result section from workbench interface as well, from this section. Okay. So let's exit it from here. This is the result section. You can get the contours. Let's say it's contour 1, and let's pick the symmetry 1, and let's pick the variable pressure for now, and let's increase the number of contours. Let's pick it 11, it's the default value, and press apply. So it shows, it aptly captures the pressure contour, pressure variation along the plate. As we move from inlet to outlet, you can see that the pressure is decreasing as we move towards the outlet, and at the inlet you can see as we move towards the wall, the pressure is increasing. Now here you can check the count of the velocity, how it's varying. Click on apply, and this is how it is varying. Let's increase the number of contours. It will give a better picture. Let's click on apply, and here we go. Zoom in. You can see the velocity at this point near the wall, near the plate, is less, and it's increasing towards the center. The velocity is also increasing as we move towards the outlet. And you can see the velocity distribution. This velocity UV and W actually represents the velocity distribution along its oriented direction. Since it is a 2D flow, so the variation would only be along its own y direction. So let's say it's along its direction. Apply. And this is how it varies. Let's see along y. Apply. This is the distribution. And density will remain constant. So this is the same color, the constant throughout. Okay, so this was the distribution. You can also see the streamline. Let's name it streamline 1. Okay, all domain start. Let's put symmetry 1 and check the contour and apply. Okay, so this is the velocity streamline. You can increase the number of points. Let's make it 52. Apply again, and you get more number of streamlines at different points. Okay, if you increase the number of points even more, let's apply it. Okay, so you can see the velocity variation along the streamline. Okay, so you can plot charts as well, like we did in the solution part. So this was pretty much it in this section, and you can go to the Workbench interface and you see the result section is also green tick. Means we have modeled the geometry, we have nested, we have given the boundary conditions, done the material selection, and we have reached convergence, we have calculated, we have done certain number of iterations, and now we are done with the result. So this was it. Thank you.